This is the talking answer key to the problem set provided online. Check how you did and see if your logic was reasonable. You can use this set to just check that you have written the correct form of the substance in the complete ionic equation, or you can do that and check your writing of balanced, complete, and then net ionic reactions, depending on where you are in your study of the subject. Some comments are also given here as to how to write the equations if you were only given the reactants to start with instead of the full equation. First, we need to determine how to write the structure of each compound when we put it into the complete ionic equation. Should it be written as shown in the first equation, as ions, or as a gas plus water? On the bottom of the page is the logic sequence I use to determine this. First, check if any of the three compounds that decompose in water are in the reaction: NH4OH, H2CO3, or H2SO3. Nope, not there. Are there any strong acids? Nope. Ionic compounds which are soluble in water. All potassium compounds are soluble, so you can see that we have three things that will now be written as ions in the complete ionic equation. What else do we have? Everything else should be written as is, not as ions or anything different. Cl2 gas is going to be written as Cl2 gas. Do not put any charges on that. H2O is going to be written as H2O liquid. We use liquid rather than aqueous because aqueous is only used for things that are dissolved solutions. Next, we need to check that we have all of the numbers correct in the complete ionic equation because we must keep the equation balanced. We have two KOH molecules or formula units in the first reaction, so that means since there's one K and one OH for each, we have two of each, which we wrote in our complete ionic equation. Next, we're going to have to see what cancels. If you have identical ions on both sides of the equation, and you have the same number of them, they will cancel out. Here we have two on the right, they're separate, and that cancels the two K pluses on the left. The result is the net ionic equation, which you see. This happens to be an oxidation-reduction reaction. I've put this here because it's important for you to realize that anytime you have a reaction in aqueous solution, you can use our rules to determine the net ionic equation. This is not one where we could predict the products given only the reactants, at least not at this point. You will need further information from the rest of the course. But sometimes when you balance the oxidation-reduction reactions, you in fact do use them in net ionic format. We need to decide the form to write in the complete ionic equation. Are the decomposable compounds present? No. Any strong acids? No. Any ionic compounds soluble in water? Yes, we have potassium compounds again. They're all soluble. And then you look for the chlorides, and they're pretty soluble too. There are only a few exceptions, and magnesium is not one of them. So magnesium chloride is soluble. The carbonates, on the other hand, are insoluble, so that one will be written as is, as MgCO3 solid. When you do the ionization with magnesium chloride, one thing sometimes somebody will do is Cl2, 2 minus, instead of 2Cl minus. You should not keep the Cl2s together there. It is two ions of Cl minus, and so you should be writing it that way. We do the same thing as we did in the last one. We're going to cancel the potassiums, cancel the chlorides. We should end up with a balanced net ionic equation, and we do. This one is a double replacement reaction. You're going to be taking, if you had to predict the products, you're going to be taking the plus ion from the first compound, combining it with the minus ion from the second compound, that's a K plus and a Cl minus, to make one of the products. And then you'll put the other two ions together to make the other product. The important thing to remember that people sometimes forget is that you must write proper formulas. So K plus and Cl minus make KCl. Just because there are two of them, two Ks and two Cls, doesn't mean the formula of the product is K2Cl2. You write the proper formula, KCl, and put a 2 in front to balance the equation, meaning there are two KCl's. In this one, we check to see if one of the three decomposable compounds are present. NH4OH, H2CO3, yes, H2CO3. We're going to write that as H2O plus CO2 in our complete ionic equation. Are there any strong acids? No. Acetic acid, the acid shown here on the left, is not one of the strong acids, so we need to leave it alone. Do not write it as ions. Just put it with aqueous after because it is a solution. How about ionic compounds that are soluble in water? Sodium compounds, certainly soluble. So both the sodium compounds are written as ions. Notice the HCO3 minus ion on the left. It is not written H plus and CO3 2 minus. HCO3 minus is hydrogen carbonate or bicarbonate. It's a polyatomic ion, and we're going to show it here written together. On the right side, you'll see acetate all the way over on the right, and that too is a polyatomic ion with all those atoms written together and a minus charge over the whole thing. Again, we cancel the ions that are identical on both sides of the equation, and we come up with still a balanced net ionic equation. This is also a double replacement reaction. It may not quite look like it right off the bat because the H2CO3 is decomposed into H2O plus CO2, but you can see from the full formula version of the equation, you have just taken the positive ion of one, combined it with the negative ion of the other. In this one, we start with zinc solid, zinc metal. This is not zinc ion, it's zinc metal and nitric acid. First, check to see if any of the decomposable compounds are in this. NH4OH, H2CO3, H2SO3, nope. Strong acids, yes. HNO3 is a strong acid, so you write it as ions. Notice the 2H plus and 2NO3 minus again. Since there are two molecules, you get two of each of the ions. How about ionic compounds that are soluble in water? Well, all nitrates are soluble, so the zinc nitrate compound is ionized. You have two nitrates. This is like the Cl2 in an earlier problem. Each one is written as NO3 minus, and then the 2 is in front. So you have two of the nitrates. The zinc here is zinc 2 plus because this is an ion. H2, as we know, is a gas. That falls into the everything else category and is just left as is. Now we go to cancel things that are identical on both sides of the equation. 2 nitrate cancels. Zinc solid does not cancel zinc ion because zinc solid is a chunk of metal sitting in the bottom of the beaker with water around it. Zinc ion is an invisible ion in solution in the beaker. They are very different substances. So you can see the net ionic equation has both of them still in it. This is an oxidation-reduction reaction of the single replacement type. In this type of reaction, if we had to predict the product, we would take the element which is the zinc here, and put it into the compound, and then take that element out of the compound and make it into its elemental form. If you have an element in your reactants that forms plus ions, it's the plus ion from the compound that is removed and put into the element form. What we can't do here is just by looking at the net ionic equation and saying, well, I can write a net ionic equation, it must be a reaction. We can't say that for this, because for oxidation reduction reactions you have to consider other things, activity series or reduction potentials. In this one, are any of the three decomposable compounds present? No. Any strong acids? No. Both of the acids present are weak acids. They are both therefore written not as ions. They are written in their full formula. Acetates are soluble ionic compounds, so we would ionize the copper 2 acetate. The phosphates tend to not be soluble, so this phosphate compound would be a solid and not be ionized. When you look back at the copper 2 acetate on the left, notice again the coefficients of the ions. Since there are 2 acetates in each copper acetate molecule or formula unit, 3 of those units would make 6 acetate ions. We look for something to cancel on both sides of the equation so that we can write our net ionic equation. There isn't anything. Everything is different. So the net ionic equation in this case happens to be identical to the equation that was given for the complete ionic equation. This one is a double replacement reaction also. The final problem, let's look and see what we have for decomposable compounds. Are there any of them present? NH4OH, yes. So we write NH4OH as ammonia plus water. Are there any strong acids? No. How about ionic compounds soluble in water? Nitrates are all soluble, so the aluminum nitrate and ammonium nitrate are both written as ions. Hydroxides tend to be not soluble. Aluminum hydroxide is the solid. Notice again we have 3 ammonias, so we're going to have 3 ammonium hydroxides, so we're going to have 3 ammonias and 3 water molecules. We have 3 ammonium nitrates on the right, so we have 3 ammoniums and 3 nitrates. We look for things to cancel. The nitrates cancel. Nothing else cancels. So our net ionic is as shown. Now, there are other ways we could have been given this problem. Suppose we were given the combination shown below. Aluminum nitrate and ammonia gas. This would indicate you'd bubbled the gas into this solution of aluminum nitrate. We have to figure out the product. Now it is a double replacement reaction, but we can't see it with just the NH3. What you need to do is remember that NH3 in water, which is what the solvent is going to be composed of NH3, water, and some ammonium ions and some hydroxide ions. You can add H2O to the left side of the equation here, and then think about the ions that you need to exchange to make the product as NH4 plus and OH minus. That would give you aluminum hydroxide as your product and ammonium nitrate, which is the correct answer. You will see then there will be a water molecule stuck on the left side of the equation, actually more than one once you get it balanced, and you can't see that in the particular way the problem was presented. This too, as I said, is a double replacement reaction. If you have had a lot of trouble with these problems, review the video, The Road to Correct Net Ionic Equations, starting from a balanced full formula reaction.